Welcome to this explainer. Today, we are taking on, hands down, one of the most fascinating engineering challenges in modern AI. We're going to architecturally deconstruct exactly how we map complex, messy relational data into strict, rigid computer memory. Because look, if you want to understand how deep learning actually models molecules for drug discovery or how it maps out massive global social networks, you absolutely have to understand how we build the container for that data first. We're essentially translating wild, irregular topologies into the strict, unforgiving language of linear algebra. Okay, let's dive into this. Here is our structural blueprint for the session. We're going to start with data beyond the grid, move into constructing the dual foundation, look at the mechanics of message passing, engineer some structural integrity, and finally, we'll talk about escaping the dense trap.
So starting with section 1, data beyond the grid, and why standard ML basically fails on networks.
You know, standard machine learning models, like convolutional neural networks, stubbornly expect all data to live on a perfect, fixed Euclidean plane. Think about it. An image is just a rigid grid of pixels. A sentence is a rigid one-dimensional sequence of words. Standard ML demands this uniform Excel spreadsheet grid where row 1 is always sitting right next to row 2. But real-world data, like the atoms in a chemical bond or the structure of a sprawling corporate org chart, that is an arbitrary, messy, non-Euclidean tree structure. Node A might have 2 connections, while node B has like 10,000. There's literally no absolute up or down in this space.
So, what actually happens if we try to force this arbitrary structure into our standard model? Well, imagine a messy corporate org chart, and then imagine a standard Excel spreadsheet. Let's try to just flatten that org chart straight into the spreadsheet. Boom. Watch what happens. It completely destroys the connections. The whole complex hierarchy of who reports to who is just gone. If you try to pad it out to make the grid work, you end up leaving millions of blank, empty cells. And this is the killer intuition for why graphs require a completely different architectural approach. Grids just fundamentally lose relational information.
Moving to section 2, constructing the dual foundation, the map and the skills.
To solve this architectural array mismatch, we realize pretty quickly we cannot use a single grid. Instead, we have to build a dual foundation. We need to separate the data's properties from its structural connections. So we start by building our first container, the feature matrix, which we call X. Think of this as the registry or the skills spreadsheet. It's wonderfully straightforward. Each row represents a distinct node, like a specific employee in our org chart, and the columns contain their attributes. You know, things like their proficiency in Python, management, or sales. This matrix holds the actual data. But here's the catch. It knows absolutely nothing about who works with whom.
And this brilliantly illustrates why we need our second container to give that data structure, the adjacency matrix, denoted as A. If the feature matrix is the skills registry, the adjacency matrix is the strict map or phone book. It is a giant, rigid grid made entirely of zeros and ones that strictly dictates the architecture's topology. If row I, column J, contains a 1, it means those two nodes share a direct structural edge. If it's a 0, no connection. By separating the map from the skills, we've perfectly translated our irregular structure into a format our GPUs can actually understand.
All right, section 3, mechanics of message passing, data in motion. Now that we have our 2 foundational spreadsheets, how do they actually interact? Well, when we multiply our adjacency matrix by our feature matrix, it triggers this dynamic physical event called message passing. Picture a central node surrounded by its neighbors. Think of a specific row in the adjacency matrix acting like a mechanical arm. Wherever there is a 1 in that row, the arm extends out to that specific neighbor. It reaches out, grabs these glowing blobs of light, which represent the physical features and data from those neighboring nodes, and pulls them back into the central node. The zeros in the matrix cancel out the non-neighbors, so the arm only grabs data from nodes it's genuinely connected to. Then, the central node aggregates these glowing blobs of data together. This right here is the absolute core of how information flows through a graph representation.
Section 4, engineering structural integrity, the normalization pivot.
Now, as architects, we always have to anticipate points of failure. What happens to our network if a specific node has a dangerously high number of connections? Let's go back to our org chart. You've got an intern with exactly 2 connections, and you have the CEO with 10,000 connections. If we simply let that mechanical arm grab and sum all the features from neighboring nodes, the CEO's node is going to pull in 10,000 blobs of light.
The mathematical value of the CEO's node is going to instantly explode. It would completely overwhelm the neural network, totally washing out the tiny feature norm of the intern's node. We desperately need a safety valve here. So to stabilize this flow of electricity and data, we engineer what's called the degree matrix, denoted as D. The degree matrix is a diagonal matrix that simply counts the number of edges connected to each node. But wait, we don't just divide by this number. We perform a critical step called symmetric normalization. This mathematically scales the messages based on both the sender's connection count and the receiver's connection count. So if a highly connected CEO sends a message to an intern, that message is mathematically scaled down so it doesn't blow up the network. This normalization is a non-negotiable structural component for stability. You just can't build without it.
So the crucial point is, there's one more massive engineering failure mode we have to avoid: omitting self-loops. If you only aggregate features from your neighbors, you actually leave your own features behind. Over a few layers, your node representations completely forget their own identity and turn into this indistinguishable mush of the nodes around them. As architects, we solve this by simply adding the identity matrix to our adjacency matrix before we normalize. This ensures every node's mechanical arm reaches out and grabs its own glowing blob of data too.
Finally, Section 5, Escaping the Dense Trap. Let's talk enterprise scale.
We have to transition from theoretical mathematics on a whiteboard to the cold, hard realities of physical GPU hardware. Because how does this architecture actually hold up at enterprise scale? Well, here is a massive wake-up call for anyone writing custom graph code. If you naively allocate a dense adjacency matrix, that giant grid of zeros and ones we were just talking about, for a graph with just 1 million nodes, it will demand 4 terabytes of memory in standard precision. 4 terabytes. There's no way. Your GPU will instantly crash. And honestly, the worst part? Because real-world graphs are incredibly sparse, 99% of those 4 terabytes are just zeros. It's totally wasted space.
Now, what's really interesting about this slide is how we actually solve this in production with a direct code math sync. On one side, we have our theoretical dense adjacency matrix A requiring squared memory and filled with useless zeros. On the other side, we have the production standard, PyTorch Geometrics Edge Index. This uses a sparse coordinate format. Instead of drawing a massive grid, it literally just writes down a list of where the ones are. It lists the source nodes and the destination nodes. That's it. This proves that Edge Index is just a brilliantly memory-efficient way of writing down the exact same adjacency matrix topology. Honestly, this single shift is the only reason we can process billion-node graphs today.
As we wrap up this explainer, I want to leave you with a bit of a provocative thought. The dual foundation we just built perfectly captures a static snapshot in time. But what about a global financial transaction network or a social media platform where the connections are changing every single millisecond? How do you re-engineer this static blueprint to handle continuous time? That is the bleeding edge of temporal graph networks, and it's a profound challenge that pushes the very limits of the architecture we've explored today. Thank you so much for joining me to deconstruct the structural foundations of graph representation.